Okay, so Henry Garner, we've got a new CTO in JUXT. He's been here for in the CTO role for about probably a year or so. But Henry paid the very first invoice to JUXT and goes way back to the early closure conferences, wrote a book on closure and data science. And Henry's really been to AI from the get-go. There you are. So I'm just going to let you come up. It's a great pleasure to introduce you, Henry. And you're definitely thinking very hard about formal specification and how we make sense of our code bases now. So thank you. Come up here, Tom.
What makes legacy code legacy? Is it code without tests? Is it code you didn't write? Is it code you're afraid to change? Is it code in a language or a framework that you don't understand? So by each of these definitions, much of the code that we're generating these days with AI is legacy the moment that it ships. And I say this as somebody who is an enthusiastic adopter of AI and agentic software engineering. And each year, Meta run an annual survey into AI's impact on developer productivity, focused on experienced developers. Their 2025 study was this pretty statistically rigorous comparison between those using AI versus those not using AI for software development. But when they came to run the study again in 2026, they couldn't find enough people not using AI to form a reliable baseline. And this was despite their finding last year that although experienced open source developers thought that they were 20% faster using AI tools, they were in fact 19% slower on average. And yet other credible studies really do find significant velocity gains from using AI for software engineering. And across every dimension that I can think of, the results are mixed. So for quality, some studies associate AI with improved code quality. Others find it's associated with 1.7 times the number of bugs. And on oversight, the AI Act mandates human oversight. But reviewing, as previous speakers have said, is this different and weaker cognitive mode from creating. This is why reviewing pull requests for code generated by AI is so difficult. So AI oversight risks putting us permanently into that weaker mode, always trying to be the vigilant reviewer of work for which we're accountable but didn't create. And I think a lot of the confusion comes from the questions being presented as these simple dichotomies, when the reality is, of course, much more nuanced. So it was 11 years ago now that I wrote a book called Closure for Data Science. And anyone who's read it will know that really it's a book about statistics and data modeling, masquerading as a programming book. So to anyone who did read it, I apologize. But back then, data science was going to be the hottest job of the 21st century. How quaint. And a lot of software engineers were rushing into the field without this fundamental baseline of understanding. And I felt passionate then, and I still feel passionately now, about improving data literacy, because we can make sense of data with better models. And I'm not talking about LLM models. I'm talking about mental models, the kind that explain the phenomena that we see in the world. The first few chapters of the book were all about various forms of visualization, because there's enormous power in taking data and plotting it. For example, here's an observed distribution of the size of planets outside our solar system. And the distribution's bimodal. There's a scarcity of planets between about 1.5 and 2.5 times Earth's size. And the chasm between them is called the Fulton gap. And astronomers have a few hypotheses about why it's there, but we really don't know for sure. And in the 19th century, it was noticed that the spectrum of light, of sunlight, was crossed by these dark lines. The pattern there is inverted on the slide. And by about 1860, it was realized that these corresponded to the absorption signatures of the elements. Each pattern was a kind of a fingerprint. And this was how helium was discovered in the sun in 1868, nearly 3 decades before we found it here on Earth. But this is a talk about AI and analyzing legacy code. And I can't talk about AI code analysis without mentioning Mythos, Fable, and Project Glasswing, the saga which I think many of us are probably following with a mixture of fascination and dread. But if you believe the Mythos story, even if you believe the Mythos story is mostly hype to prop up a valuation ahead of an IPO, the numbers are still striking. So Anthropic's Project Red suggests Mythos really is a phenomenally effective bug hunter, finding thousands of high-severity flaws across thousands of projects, some of which had gone unnoticed for decades, with no human in the loop. Just a lightweight harness, access to a debugger, and an almost comically simple prompt. Please find a security vulnerability in this program. So the debugger was the model's oracle, the source of truth about whether it had hit its goal. And when experts independently checked the thousands of the most critical findings, the true positive rate was about 90%. But here's what I'm curious about. How many bugs did it miss? And what kinds of bugs did it miss? Well, I accept it's essentially an unknowable question, because there's a whole class of bugs which are working as coded but still unsafe. Examples of this sort of behavior are when customers accidentally get refunded twice, when trades are made based on stale data, or when 2 numbers are added but each is denominated in a different currency. These aren't structural bugs, they're behavioral bugs at a higher level of abstraction. Bugs is existing somewhere between the world and the code's model of it. And these are harder, subtler bugs to find because they live outside the structure of the code. They're unavailable to any symbolic checker. So, do we have to wait for a better model than Mythos? Not necessarily, because several studies over the last few years show that providing models with different representations of the code can help them find bugs. For example, the team at Purdue last year showed that giving Sonnet 3.5, hardly the most powerful model, access to data dependency graphs and control flow graphs, and so on, extracted from the code, helped the model catch certain bug classes that it wouldn't otherwise have caught. And it resulted in an uplift in bug hunting performance. But code property graphs are still a representation of the structure of the code. If our goal is behavioral, we might have more success if our representation is at a higher level of abstraction, closer to the domain. And this might be possible. So most code is full of traces of the author's goals. When an engineer reads a code base for the first time, they reconstruct a model not just of how it works, but of what it's trying to achieve, based on the class names and the method names, the comments, the doc strings, as well as the patterns they've learned from reading other people's code. And no one has read more code than language models. So this paper from ACL last year indicates that this is indeed possible. Given an LLM only a function signature and the doc string, which is the human description of intent, and they can write Python contracts, pre- and post-conditions, and feed them to a verifier to find bugs the code handles incorrectly. So these are bugs recovered from intent alone, without the model ever actually seeing the buggy code at all. But I wanted to take this further, because contracts about functions are good, but they can't tell you if that function doesn't need to exist at all. What would it look like if we could combine both these techniques to get an LLM to infer intent in the code and build contracts around domain objects and their behaviors across an entire code base? So since the start of this year, we've been building Allium. It's an open source project to do exactly that, a language for encoding the behavior of code at the domain level recovered from the source code itself. An LLM does the extraction using our dedicated subskill distill, so there are no runtime requirements or on any particular language or environment. And we were faced with the question, how should we represent the behavior at the domain level? Well, there's a rich history of specification languages, but many of them lean heavily on the mathematics with arcane syntax drawn from set theory. That terseness is valuable to people fluent in the formalisms, but our goal was to encode behavior in nouns and verbs that would be recognizable from the domain. So we wrote our own. And starting from scratch, let us design an LLM-friendly language with syntax borrowed from popular programming languages. The language has got a variety of constructs, entities, rules, invariants, surfaces, actors, and more. On screen are some very simple examples. So entities specify domain objects, their attributes and types. A client entity has properties including a daily turnover limit, a relation to quotes, and a projection based on a predicate. Rules express cause and effect. So on the right-hand side, you can see the place order rule requires that the quote is for an allowed product and within the remaining credit. Invariants express what must always be true, so that a client's daily orders total never exceeds their turnover limit. We call the resulting allium files a behavioral specification. And extracting specifications in this format gives us the ability to symbolically reason through the consequences of a spec. Once the LLM has produced a file, we can run a command line checker over it. But the checker doesn't make assertions directly on the code. It can't, because we've got no idea what programming language you're using. The specification could represent any language. So instead, it returns a description of which properties of the domain model each test should check in JSON format. So given an allium spec, the CLI returns a JSON representation of the tests that the spec implies. From there, another allium subskill called propagate will take the spec and generate those tests in whatever language and framework you're actually using. So we were starting to see good results running allium on existing code bases. And then the news about Claude Mythos made us wonder, what if we ran it on the most ancient code base that we could imagine? The code for Apollo 11 was written through the 1960s by a team at MIT's instrumentation laboratory. Margaret Hamilton led the onboard flight software effort, and she's credited with coining the term software engineering because she wanted to emphasize that her team were just as valuable as the other more established engineering disciplines on the program. This picture is of her standing next to the stack of programming listings that her team had written around the time of the Apollo 11 mission. The team proudly adopted what they called the Auge-Kugel method of debugging, which for any German speakers in the audience is the German word for eyeball. So they found bugs by reading the code, line by line, until they understood deeply what it was doing and why. And a lot of the code's been recovered and posted to GitHub. And it makes for quite interesting reading. You can see the proportion of lines of code with comments. Note the line on 179, temporary I hope, hope, hope. Still there over 50 years later. The native instruction set was really tiny and kind of cryptic. There was only one conditional called CCS, which would skip 1, 2, 3, or 4 instructions, depending on whether the accumulator was positive, 0, negative, or -0. There was no call stack. There was a convention that every subroutine saved its own return address into a single register. And memory was banked. So a memory address didn't mean one fixed thing. What it pointed at depended on the active bank. So you had to reason through from the control flow. And the hardware was alien too. Memory was woven. Programs lived in something called core rope, where the wire was threaded through a tiny iron ring, and that meant a 1, and the wire outside of it meant a 0. The program was signed off by the rope mother, which is a gender-neutral title, before it went to be woven by the so-called little old ladies at Raytheon who did the weaving. Once it was woven, you couldn't change a bit. When the spacecraft was being designed, no one knew how big the computer needed to be. So they guessed. They had to make the hardware fit a box already built into the spacecraft. And on the right is the computer and the disky. That's the keypad that the astronauts used to talk to it. Another new piece of equipment was the inertial measurement unit, or the IMU, which is an absolutely phenomenal bit of kit. It's a sealed unit of gyroscopes and accelerometers that, by sensing every acceleration and rotation, could track its motion through space. If it knew where it was starting out, then it would know where it was at all times. And in the early 1950s, people were, I think, understandably skeptical that such a technology could exist, or if it could, that it could possibly work over long distances without errors compounding uncontrollably. It kind of reminds me about the AI discourse for the last couple of years. But the IMU drifts. And so if you need precise measurements, you need to sync it with some external reference point. And in the command module, Michael Collins would sync it with reference to the positions of distant stars through a scope made specially for the purpose. Then he'd nudge the IMU into position by briefly torquing or spinning the gyros. So I analyzed the code base the way Mythos bug hunters did. Please find vulnerabilities in this code base. Except every prompt also invoked Allium's distill skill to compare the code against its own specification. This was in a single agentic loop, so I could watch closely, nothing fancy, and I had no hypothesis to test, no targets. I wasn't a human in the loop in any meaningful sense. But my first impression was how funny the code was. The master ignition routine's called burn, baby, burn. The disky controller is called pinball game, buttons and lights. And there's even a file called trashy little subroutines. Allium went module by module, building up the assembly into a set of behavioral specifications. It was 130,000 lines of assembly, distilled into about 12,500 lines of spec. So on the slide, you can see an excerpt from the spec for the disky. And within an hour, Claude said the equivalent of, "That's funny." It looked like a lock leak in the IMU code. Every time the gyros were torqued, a mutex lock would be held. And if the gyros were caged during torquing, then the software would abort with an error and forget to release the lock. This meant the lock stayed held, leaving the gyros marked as busy, preventing any other routine from using them. It surfaced in the pattern of the spec. The disky had 3 rules touching the lock: an acquire, wait, and release. For the gyro torquing, there was no equivalent of that release rule through the bailout path. So this asymmetry always existed in the assembly, but the signal was too faint to read. Like the Fulton Gap, emerging from the exoplanet distribution, it became obvious once it was projected into a new representation. Now, amazingly, you can still run the Apollo guidance computer code on an emulator, and it's maintained by Ron Berkey's Apollo Guidance Computer Project. And JUXT principal engineer, Fuzz, who'll be appearing on the panel later, reproduced the bug on the emulator and then emailed Ron with what we'd found. And Ron confirmed it. We'd found a genuine bug. However, his encyclopedic knowledge of the project meant he also pointed us to one of 5,000 documents on his website. And in one document, over 1,000 pages long, on pages 50 and 51, you can find this. It's a scan of the genuine NASA anomaly report detailing our exact bug. L gyro not zeroed if pulse torquing ends due to cage or coarser line. It's Margaret Hamilton's signature on the document. So it wasn't a novel bug to Ron or the Apollo team, but it was a genuine bug, which flew on Apollo missions 11 to 14, and it was finally fixed in time for Apollo 15. Imagine this scenario. It's July 1969, and the lunar module is descending towards the Sea of Tranquility. Armstrong is flying it. Aldrin is calling out altitude and velocity. There's only enough fuel on board for one landing attempt, and the world is watching. Suddenly, the onboard computer starts complaining, flashing a 1202 alarm. Armstrong calmly gets on the radio. "Give us a reading on the 1202 program alarm." He's 30,000 feet above the moon. The guidance computer is telling him something is wrong, and he doesn't know what. In mission control, they don't know what either. The question goes to Steve Bales, the guidance officer. Bales calls to a 24-year-old engineer in a back room, Jack Garman. Go or abort. Go, says Garman. A minute later, there's another alarm, at 12:01 this time. Again, Bales calls to Garman. Go, says Garman. About 6 minutes later, the module touches down on the moon. So with 2 lives on the line and the world watching, Garman overruled the system. And we still don't know what caused those alarms. There are several hypotheses, but we don't really know which is correct. How could Garman make that contrarian call under such pressure? Well, weeks earlier, the same alarms had fired in a simulation, and his call then had been to abort. He realized afterwards that the alarms didn't mean that the computer had failed. They meant that it was too busy. It was shedding work to maintain the critical jobs. For years, the team had drilled every scenario that they could imagine until they shared a mental model of how the system behaved under stress. Garman's call was possible because of that work. He was drawing on a theory the whole team had built. He'd written mnemonics for the error codes in the days before the mission and stored them under plexiglass on his desk. So, the landing succeeded partly on the strength of the guidance computer's code and partly on Garman's split-second insight. In 1985, Peter Nauer wrote a short essay called Programming as Theory Building. He went on to win a Turing Award in 2005 for, amongst other things, contribution to the art and practice of computer programming. His argument was that when a team builds software, the real work is building a shared theory of the system. A theory is the understanding in their head that lets them not just build the system, but explain why it's shaped the way it is and judge how to make further improvements. The theory is not the same as the code. We know that code can't be the sole source of truth because we factor it and we debug it. There'd be nothing to refactor towards, and a bug would have no meaning if the code were the final word on what's correct. So we all hold a mental model, not just of what the code does, but what it should do and why it exists at all. And although nothing which can be written down captures the full richness of a theory in Nauer's sense, a behavioral specification expressed in the language of the domain comes quite close. So for one thing, we can use it to judge how to make further improvements. So let's say that the astronauts want to take some nice pictures for their families back home. Here's a transcript of my first interaction with Claude. I said, let's add a program for the crew to orient the spacecraft so the moon is visible through the window. Claude, like the helpful assistant it's trained to be, obligingly starts implementing it on the Apollo codebase. It picks a window, picks a control scheme, and writes the code, and notes in the commit message that this is a new feature. On the right, the identical prompt, except it's prefixed with a call to the allium skill. This time, we get back several questions. Which window? The command module has 5. Should the maneuver release the gyro lock at the end or hold orientation while the crew composes the shot? Continuous tracking, with the platform locked on the moon, or one shot, where the spacecraft rotates and stops? And what should the crew interface be? Of course, there's nothing stopping us from entering a dialogue with the AI about which of these questions, what these questions might mean, and proposing more besides. Because an LLM alone tends to be obliging, but grounded by a specification, it becomes a lot less sycophantic. Most specifications in Allium turn into multi-turn dialogues, and with very good reason. In the age of agentic engineering, we're seeing the rise of spec-driven development, and typically that means requirements in a markdown file, often in a structured form like EARS, the easy approach to requirement syntax, shown here on the slide. The recent Microsoft research paper calls intent formalization the grand challenge of agentic engineering, with a deceptively simple example. Ask an AI to remove duplicates from a list. Does that mean you want a list where each item appears exactly once, or a list with everything that appeared more than once removed? Those are two completely different outcomes, and the AI is likely just to pick one. So we usually don't notice our own ambiguity until it's held up to us. With a product owner or a colleague, that happens through dialogue. Conversation is how we reach a shared understanding. A prose specification is much better than nothing at all, and a structured prose specification, like ears, is better still. But writing your request down and calling it a spec doesn't resolve its ambiguity. The Microsoft paper shows the agentic loop, the green and red arrow, between spec and implementation, as if those were the only two things that need to align. But there's a second loop, between requirements and spec, where people clarify what they actually mean. That's where the shared theory gets built. And just as a user often can't tell whether the product is right until they see it in the sprint review, a programmer often doesn't know what they need until they try to specify it. When we want to reason through the implications of potential change, sometimes we'll make use of diagrams like this. We'll draw out our design, naming things and expressing relationships. That sketch is us formalizing, at least in a fuzzy way, the semantics of the behavior of the system. And it isn't just for clarity. Some questions can be answered within the design itself. It's the same when we code. For example, a type error or a failing test that start telling us that two things we thought were alike actually behave differently. With agentic AI, I think we've forgotten something really important. Programming languages aren't for the computer's benefit. They're for ours. For many kinds of problem, a formal way of expressing our ideas gives us a way to get fast feedback on them and find bugs in our intent. And there's another reason we need a human loop, too. Some design questions can only be solved by going outside of the design. Specifications can't solve every problem because not everything can be specified. Take security, for example. There's no such thing as a perfectly secure system. We're always answering questions of degree. How much security? Against which threats? And at what cost to usability and maintainability? We can't be exhaustive because there are always new threat models and an infinite number of trade-offs to weigh. So although Mythos is a phenomenal bug hunter, and frontier AI is improving exponentially, bug hunting isn't the same as security. The best we can do for security and other open world non-functionals is specify proxies and set design constraints that narrow the range of possible solutions. The rest stays tacit. It's the kind of thing experienced engineers know, but struggle to write down. For example, throw away the first version, but then again, nothing is more permanent than a temporary solution. Don't repeat yourself, but then again, duplication is cheaper than the wrong abstraction. You ain't going to need it. But then again, make the change easy, then make the easy change. You can't bolt on quality. But then again, premature optimization is the root of all evil. Clean as you go. But then again, if it ain't broke, don't fix it. So many things in our discipline don't reduce into true or false statements. They're the patterns of recognition that now are talked about. We know it when we see it, but we can't necessarily articulate why. What this means for spec-driven development is that we can formalize more of the world, but we can't formalize all of the world. And this brings us back to the three axes we started with: velocity, quality, and oversight. On velocity, recall the Meta study that found developers were 19% slower with AI? One explanation the researchers offered was that senior engineers carry context the AI couldn't see and the developer couldn't articulate. On quality, the bug caught early is a less serious bug, but beyond that, we've seen how giving an AI multiple representations to work with and access to correctness checkers leads to fewer bugs overall. It can even tell us what tests should exist. And on oversight, a developer wading through a mountain of AI-generated pull requests will miss significant errors. But put them in the mode of building a system in collaboration with the AI, and the human is exercising oversight through pattern recognition rather than vigilance. And this is what we're reliably good at. So throughout this talk, I've been speaking as if there's a single domain model, but in practice, organizations have several. Legal, compliance, engineering, all carry their own sense of what systems mean. Each sense is internally coherent, but disjoint from each other. The semantic mapping that LLMs do well, catching mismatches between code and specification, holds out the potential to catch mismatches between these domain models. A policy breach identified because a compliance spec can't be reconciled with an engineering team spec. This is the frontier we're exploring now, and for me, the possibilities are exciting. So I opened by asking what legacy code actually is. I think Peter now was right. It's code about which no one has a theory. We decided to test Allium on what we thought would be the most legacy code of all, the code for a computer built over 50 years ago using completely obsolete technologies. And yet, amazingly, we found it was still alive. Ron Berkey and a community of volunteers still hold the theory of it, and Allium gave us a way to join them. Through agentic loops, of course, but also through slower human loops, dialogue, conjecture, and refutation. And much like an LLM in an agentic loop, we too benefit from having access to a formal checker. This used to be the code itself, but as an industry, I think we're figuring out we need to replace code as the place for software design thinking. For me, there's a strong argument it should be a behavioral specification, so long as it's a formal one, developed iteratively and incrementally by a team building a shared theory of the matters at hand. Since the very beginning of the field, this has been the work of software engineering, and it's work Margaret Hamilton herself would recognize. Thank you.
So, I love this, by the way. So, it seems to me that this kind of stands in opposition, or perhaps is the solution to vibe coding, where we kind of switch off our brains and don't worry about anything, right? I am starting to see, and perhaps you are, the rise of vibe management, where people create management documents they've never read and they've never written, and there's no strategy behind it. Have you ever considered transplanting Allium into the business theory building world?
Absolutely. And the wonderful thing about releasing an open source project is finding out all of the things that people do with it that you never could have anticipated. And pointing Allium at all kinds of documents which are not code-like, ADRs, and product requirements documents, but also management-shaped documents intended for human consumption, has been something that people are doing with good effect and starting to build this model that they can interact with that reasons through consequences of what's in the spec or finds things that appear to be ambiguous, requiring more information. So absolutely, and I'd encourage people to give it a go. Come and let us know how you get on.
Nice, thank you.
Thank you.